Can you hear me? Okay, welcome to the discussion session, Strings and the Real World. After all, that's the aim of string theory, hopefully, to make contacts with the real world. So there are four of us on this panel discussion that the string organizing committee has selected. I'll be chairing this session, and then we have Miguel Montero, Thomas Van Riet, and Shetan Krishnan, who are going to be panel members. They have given a general overall structure that we have to follow, which is basically each one of us gives a 7 to 10 minute kind of presentation with maybe 1 or 2 questions for each, if you have any questions, at the end of each one of our talks. After we finish the talks, then we're supposed to suggest some discussion topics that we will discuss during our presentation, and then we leave the discussion suggestion for the topic for discussions on the screen here. But of course, you're welcome to discuss those or other topics, and we will open for discussions that you can raise. In the discussion session, I would perhaps suggest that if you have any specific question to a specific member of the panel, please mention whom you're asking it from. If it's to all of us, you can just say to all the panel members, or if it's not a question but a comment, just say it's a comment. And that would be probably easier to direct it that way. The discussion session is supposed to be informal, so you should feel very free to participate, and that's the reason they have divided it to these parallel groups so that we have less participants. So that's what I'm told is the idea of having parallel discussion sessions. And that's the basic structure. So with that, I guess I think we can start. So the first one that present. So we're going to present our short discussions, short topics is by the order we are sitting here. And so the first one will be me. So I'm going to talk about these things first. So in trying to describe the real world, we have learned that the effective field theory parameters and the couplings seem to be unnaturally fine-tuned. And this puts in principle the question what does one mean by naturalness, because things seem to be fine-tuned, and the usual notion of naturalness seem to fail in a number of areas which are crucial. For example, one thing which is naturally important for us is these kind of question: why is the cosmological constant so small? That seems to be arbitrarily, unnaturally fine-tuned. Or what is the reason for electroweak hierarchy? Or what is the CP violation parameter so small, or theta angle so small in the strong sector? Why is the rank of the standard model gauge group so small? And these are just among some short list of them, but there's actually a much longer list, and this you can see that these are important questions for connecting whatever we do to the real world. On the other hand, in string theory, which is a consistent theory of quantum gravity, we have learned that we only get very selected, very special things as solution to string equation, or what we call the string landscape, which is very finely tuned. So it's an opportunity. The unnaturally fine-tuned string thing could be explaining a new notion or new paradigm for naturalness, which one may want to explore. So, since string solutions are examples of consistent quantum gravities, we can use that to gain insight about perhaps what are the overarching consistency conditions for effective field theories. And this Strongland program is to delineate the restriction placed by quantum gravity or consistent quantum gravity on resulting effective field theories, which emerge in the low energy limit of quantum gravity. And this has led to a new paradigm for naturalness, for effective field theories in the context of quantum gravity. So we have learned many principles related to this, and some of which we have understood better by arguments related to black holes in particular. For example, that there are no global symmetries. This is related to triviality of the cobordism group, the lack of topological operators, and completeness of spectrum. This was discussed in detail by the talk by Tom yesterday. Another one is distance or duality conjecture, which suggests that at extreme large limits or distances in field space, we get weakly interacting spectrum of particles whose mass scale like exponential of the field distance in field space. So that's with some exponent, which is of order 1 in Planck units. In the context of de Sitter or ADS, this translates to the statement that the mass scales like some power of the cosmological constant with a power of order 1. Again, this is the kind of things we have seen in all the string cases, and there are some heuristic arguments why this is not unnatural. Another thing, example of these swampland conditions is the weak gravity conjecture, which was briefly mentioned in Tom's talk, and also festina lente, which is going to be discussed more in the talk, in discussion today by Miguel. It basically suggests that the decay of black holes not to lead to naked singularities puts the bound on the masses of the charged particles, certain bounds. So for example, there must be a charged particle whose mass is less than its charge. On the other hand, all the charged particles have a mass which is bigger than the dark energy in the context of the quasi-de Sitter geometries to the power of 1/4, for example. And then there are conjectures related to the de Sitter. What kind of de Sitters can exist in string theory? These are go under the name of de Sitter conjecture or Transplanckian censorship conjecture, which basically try to raise issues that we have noticed in the conflict of trying to construct de Sitter, which is the difficulties in getting quasi-de Sitter solutions. So now, why would we, if the swampland condition only put restrictions, we might ask, okay, we're never going to get very specific answers to questions of quantum gravity, only some restrictions. But actually, sometimes that's good enough to actually give you predictions, and I'm trying to illustrate that in this case with the paper that we just wrote with Miguel and Irene, which was, let me just bring it here, yes, which was based on trying to understand, or more precisely, trying to draw consequences from the fact that the dark energy is so small, 10 to the minus 122. So from what I just told you in the context of distance conjecture, this means that there must be a tower of light states in this context. And you can argue that the exponent of this should be between 1/2 and 1/d. And in the case of d equals to 4 dimensions, we find that the lower bound is 1/4. And moreover, the light modes cannot involve light string state by observations. And so, therefore, since the light modes cannot be string modes, and this leads to a description in terms of KK tower, and other observation, in particular, the fact that the cooling of the neutron star cannot be too fast, puts a restriction on how many dimensions could be larger, and one finds that the only possibility is the existence of one mesoscopic dimension. So these ideas which come from swampland lead to a unique corner of landscape, not just as particularly, just choosing as a random choice, but actually forcing us to find this unique corner, that there is one mesoscopic dimension. The length scale of the order of micron range, let's say between 10 micron and 0.1 micron as a prediction. This leads to higher dimensional Planck scale much above the weak scale, but unlike the large extra dimension scenarios, whose motivation was trying to bring down the Planck scale all the way down to the weak scale, which is not our motivation, one finds the higher dimensional Planck scale is not the weak scale, but actually 10 to the 9 or 10 to the 10 GeV scale. The KK tower leads naturally to a candidate of sterile neutrinos, which is around the electron volt scale. And the standard model should be localized on a brane, because otherwise you find too weak a coupling, gauge coupling for the standard model. So you have some kind of an extra mesoscopic dimension, and the gut brane will be somehow localized. Now, the fact that the cosmological constant is positive suggests that there are sterile neutrinos, which are fermionic in the bulk, which could couple to the degrees of freedom on the brane, and this leads to the coupling which leads to the neutrino mass, which relates to the Higgs wave squared over the higher dimensional Planck scale, with some coupling which could easily give you the right range for the neutrino mass scale. In fact, if you insist that there is no hierarchy in the neutrino sector, if you assume that the sterile neutrinos and active neutrinos have similar masses, that means the neutrinos which are in the bulk and the neutrinos which pick up the mass by coupling to them, then you actually get a prediction for the Higgs wave, which is in the 10 to the 1000 GeV range. So, in some sense, we are connecting all these things together just to the dark energy, if you assume the lack of hierarchy in the neutrino sector. So, it is interesting that this leads to some kind of a unification between all these strange parameters that we have seen. The length scale, the macroscopic length of our universe is the Hubble length, which is lambda to the minus 1/2. The mesoscopic dimension would come out to be lambda to the minus 1/4, and the microscopic ones, these are Planckian scale, lambda to the 0. And then the neutrino mass scale, both the active and sterile, goes like lambda to the 1/4. The Higgs wave will go like lambda to the 1/6, and the higher dimensional Planck scale goes like lambda to the 1/12. So this actually gives you a unification of various hierarchies, all in terms of the dark energy. So the dark energy will lead to a realization of Dirac streams, where all scales are specific powers of the dark energy. It is quite remarkable that with these choices, which we are forced to by the consistency conditions and observation, this is basically very close to current experimental bounds on 1/r² experiments, which is up to now checked up to 30 microns. So this is right within the boundary of what these kind of things could be probed at. So let me just put some discussion topics that we can discuss further. So one of the things I would suggest perhaps as a topic is Swampland conditions have been tested mostly in the supersymmetric cases. We have some examples of non-supersymmetric checking of the principle, but clearly the most interesting application will be in the case that we have no supersymmetry. How reliable is our extrapolation to non-supersymmetric cases, and how can we develop techniques applicable to non-supersymmetric cases? Can topological ideas help bring some robustness to it? The same kind of techniques that have been proven powerful in the context of quantum field theories recently, perhaps they have some resonance in the context of gravity theory as well. And the second question is, can we realize the dark dimension scenario in the string theory landscape? There are similarities to the large volume scenario, but can we actually come up with a construction which give you such scenarios that we are being forced to have? So I will stop here and I will open up to questions if you have any questions. Yes?
Hi, thank you very much for the nice summary. I've got two questions which aren't, they're unrelated to one another. One question is, can you comment on how the assumption of a hierarchy among the neutrino masses will affect the results of the analysis that you just described?
The assumption of hierarchy?
Yes.
You're talking about the weak hierarchy?
Yes.
So here we have two different kinds of hierarchy. One is what I would call the cosmological hierarchy, which is why the dark energy is small. And the other one is the weak hierarchy, why is the weak scale small. We were taking the viewpoint that the dark energy hierarchy, cosmological hierarchy, is what is the fundamental thing that we want to address, which is what we address. However, as an offshoot of that, we end up with the following surprising, unexpected statement that if you assume that somehow the bulk dynamics interacts with the brain dynamics in such a way that the Higgs wave on the brain does not give you a hierarchy in the neutrino masses. You see, one of them is going to be the neutrinos which are on the gut. These are the active neutrinos. And then there are neutrinos which are outside, which is the sterile neutrinos. If you assume there's no hierarchy between them by some communication mechanism, something like the impedance matching between the bulk and the brain, then it fixes the Higgs wave. Of course, to come up with the scenarios which does this, it needs to be done. We didn't come up with the scenario, but assuming that we get a width for the Higgs, which is, again, in the right ballpark.
Okay, thank you. Second question, very, very quickly. Can you comment on how, I think you said in the last slide that the dark dimension scenario and the LVS are similar?
The dark dimension scenario is what?
Similar in spirit to the large volume scenario?
No, I'm just saying that sounds like what we want. Namely, not necessarily exactly the same parameter range that we want. We want to have constructions which have some large volume. In this case, one-dimensional, really. One-dimensional direction being large, not the whole one.
I see. Thank you.
Okay, so maybe one last question from Liam, and then we move on to Miguel. Yes, Liam.
Thanks for the nice summary. Could you comment on some of the preferred scenarios for early universe cosmology in the dark dimension setting?
Yes, actually, that's I should have said that that's exactly the area, an area we are exploring in a collaboration with a bunch of us here and some of them not here. But that is actually quite potentially an exciting opportunity for the following reason. You see. One of the main puzzles depends on how early the universe we're talking about. One is the pre-Big Bang and one is the post-Big Bang. The pre-Big Bang we don't address, we don't focus on here, but the post-Big Bang, and in particular the fact of the coincidence that the matter radiation density equality coincides with the emergence of the dark energy scale being prominent. The fact that they coincide is a surprise, this coincidence problem. And they all happen at the electron volt temperature. So this sounds very much potentially related to this mesoscopic dimension, which is also at the electron volt scale. So potentially it has some opportunity there, as well as some connection potentially with the H0 problem, because that's precisely the temperature where one needs energy injection around the electron volt scale to potentially resolve the H0 tension. So there are these opportunities for the cosmology which we find quite tantalizing, but we are still in the process of working them. So perhaps we can move on to Miguel's presentation.
Okay, thanks very much. I'd like to start by thanking the organizers for putting together this super nice conference and for inviting me to be part of the panel. So, Cumrun just told us how naturalness is not such a good guiding principle if you're doing things in quantum gravity. And he gave us some concrete scenarios and the general fact that you can get guidance from string theory, but if you cannot use naturalness, and naturalness is intrinsically related to symmetries by the notion of technical naturalness, what can you use to guide you in the search for interesting models? Well, one point that should be emphasized, I think is very important, it was already emphasized yesterday in Tom's talk, is that you can learn a lot, not just from the presence of symmetries, but also from their absence. So it's a win-win situation. You either have symmetries, and you have anomalies, and you can construct theories, or you don't have them, and you can use things like the completeness principle. Okay, so just to review briefly what that is, if you have any low-energy effective field theory coming from gravity, you typically have operators you can construct in your effective field theory, like Wilson lines, can be line operators, surface operators, or also point-like operators. And you have them in your effective field theory. There's no way around them. What quantum gravity and the completeness principle tells you is that these operators must be allowed to end. So this thing is part of effective field theory. Requiring that they must end in some other operator is giving you new operators in the theory. And that can be interesting, that can be powerful, that can be constraining. We have examples of how to do that in higher dimensions supersymmetric theories. But since this is the strings and the real world discussion, what I wanted to bring up a little bit is how can we apply these ideas to learn stuff about a real world, about the standard model, without assuming anything in particular about what's the string completion. So just a very simple example, which is not that new. Suppose that you want to have an axion, a QCD axion to solve the string QCD problem. Then the completeness principle tells you that you must have strings that couple to the axion. And we can learn stuff about these strings just from doing anomaly inflow. So we can learn about the degrees of freedom of these strings. And this idea you can repeat. The standard model has line operators, and these line operators must end. So the completeness principle tells you there has to be monopoles. And precisely what are the charges of the monopoles is related to this question, which is what is the global form of the standard model gauge group. We know what the algebra is. We have seen this at LHC, but we don't know what the global form of the group is. You can also try and apply the completeness principle at the level of local operators. And then you're going to learn that you must have some instantons, some amplitudes, and related to that, some new anomalies that you get by evaluating the partition function on singular manifolds. Things that you're not supposed to do in an effective field theory, but which the completeness principle tells you can do in quantum gravity. They can give you new anomalies. So for instance, there's some symmetries that people sometimes use to constrain to try and protect the proton from decaying, like triality or exality. They can have new anomalies by looking at these singular backgrounds are not part of the effective field theory. Effective field theories would never look at this, but we know we can. And a particularly exotic but nice application of this is that if you take the completeness principle to the extreme, if nothing has a conserved charge, that means nothing, not even space-time itself. And the manifestation of that is that you must always have end-of-the-world membranes. For any quantum gravity vacuum, this is explicitly true in many string theory examples. And so something like that should be true for the standard model too. So there should be an allowed boundary condition for the standard model. And that, of course, gives rise to all sorts of interesting questions. What is the tension of this guy? Can it nucleate? Can it produce a bubble of nothing? What are the local degrees of freedom there? So just from kinematics, this slide was all kinematics. You can learn a lot by applying these principles to the standard model, and it's something that hasn't been done systematically so far. But as we learned from Tom's talk yesterday, if you make things a bit more strong, if you just not say that global symmetries have to be broken, but you try to quantify how much, you learn many interesting things. So yesterday we learned about how you can get something like the weak gravity conjecture, just from demanding that certain symmetries are broken sufficiently strongly. And in connection to this, I wanted to bring up a line of work that I've been pursuing for a few years now with Thomas, Herben, Cumrun, and which has gathered some of the people interested, which is we try to generalize the principles behind the weak gravity conjecture to the Zeta space. So we look at black holes, big black holes, so-called narrow black holes evaporating in the Zeta space, charged narrow black holes. And what we find is that if you want these black holes to evaporate nicely back to empty the Zeta space, just like their flat space or ADS counterparts do, there's a non-trivial bound on the spectrum of the theory, which we call the Festina-Lenti bound, which I've chosen to write in this form. So here, Hubble is the Hubble constant. Alpha is the fine structural constant of some U1 field. You have a U1 field like weak gravity. M is and M and Q are the mass and charge with respect to this U1 of every charged particle in the spectrum. So we are claiming that in a consistent quantum gravity in the Zeta, the vacuum energy is upper bounded by this thing, okay? Now, you can check against the real world. What does this say for the real world? Well, if you just use the electromagnetic U1 on the electron, it predicts that the vacuum energy is less than 10 to the minus 88. Now, it's not quite what we want. It's not 10 to the minus 120, but it gets us 3/4 of the way, okay? When you have a statement like that, the basic feeling you get is like, yeah, it's going to be ruled out easily because it's really strong. So for instance, one thing that it doesn't like is non-abelian gauge fields. Non-abelian gauge fields have gluons. Gluons are massless. They violate this bound. To get around this, it must be that every non-abelian gauge field in the Zeta, according to this bound, must be either Higgs or confined at a scale above the Hubble scale. And as we know, this happens for the non-abelian gauge fields of the standard model, okay? The bound is quite predictive. You can use it to, for instance, constrain models of dark photons. So this is a figure from a paper that is coming out tonight, tomorrow morning in Europe, where we just apply this bound to situations where you have some dark photon, it's a candidate for dark matter, which has merely charged particles, and they couple to the standard model. And the lines that you get from the bound are competitive with, astrophysical constraints, known laboratory exclusions, and even they can discriminate regions of parameter space which are going to be probed in the future. So it's quite exciting. So what are the questions that I want to bring up for discussion in the context of all of this, for us to discuss later? Well, this is, I think, a very important point. Is like, sure, global symmetries must be broken in gravity, but exactly how much? This was the point of Tom's talk. He had a discussion about this point yesterday. Here I want to take a slightly different angle, which is to ask the bootstrap for help. In particular, there's this nice paper recently where they were able to tie together in a rigorous way from the S matrix in flat space the cutoff of the effective field theory to the coefficient of certain higher derivatives terms in the action. Now, this is what you would expect, but they show it rigorously. There is this new development from the side of symmetries, which is all these new things that are happening about symmetries that are non-invertible. So in quantum gravity, you expect this to be gauge or broken. And so far, we haven't explored a lot the mileage that we can get from that. It would be nice to do so. And more generally, we really need to understand what are the mechanisms that string theory can provide to shed issue on naturalness issues. So for instance, the Festina-Lenti bound that I gave you before is really producing something which looks very unnatural from the effective field theory. It's putting an upper bound on the cosmological constant, which makes it very fine-tuned. And something I'm personally very interested in is, can we give better evidence for the Festina-Lenti bound? We gave some mild evidence for it in string constructions. Can we make it stronger? This is a point that I'm actively thinking about right now. So with that, thanks for your attention. And if there's any questions, please just ask.
Maybe one or two questions at most for me.
You tested your bound with the electron mass. I want to ask you, how does it look like if you take the lower bound for the neutrino mass that we have now?
Yeah, that's a great point. So if you take the neutrino, I mean, you shouldn't take the neutrino, right? Because it's not charged under a long-range gauge field in the sitter, but if you just go ahead and do it, you on the nose get 10 to the minus 120. And this is related to the point that Cumrun was explaining, that there's a coincidence between the neutrino mass scale and the cosmological constant. So we thought hard about trying to argue that we could connect these things, but I don't know that there's an argument that we can do that.
Any other questions? I have one question. What are the briefly, if you can explain, connections between festina lambda and inflation? What kind of bounds does it give you?
Right. So the one thing that one can say from the get-go is that just the standard model, the standard model by itself is not compatible with festina lambda and inflation on a high scale. And it's simply because, Hubble during inflation is much higher than the electroweak scale, so the fermions are effectively massless. So that means that you need to change it. So one scenario which is favored from this point of view is Higgs inflation. Another thing that you can do is you can take a gut model where the gut scale is such that so that the gauge fields are confined during inflation. So there's several scenarios one can take into account. There are several ways out. So far, it seems difficult to favor one versus the other. What you know for sure is that the standard model, vanilla standard model, is not compatible with this inflation.
Okay, let's thank Miguel again.
So I also would like to join Miguel with thanking the organizers for a very nice conference so far. So I will simplify the discussion in the sense that there will be no standard model, and I want to ask the most simple questions, okay? So imagine that the critical superstring is useful for phenomenology, then the most trivial things we need to obey is to try to get a four-dimensional world, and there are two ways, at least when you stick to a geometric framework. So one is you say, okay, we have 6 compact dimensions, and another one is we think in terms of brane worlds. So I will not discuss the second, but maybe it's good to bring it up during the discussion. So let us, for now, stick to the first option, right? So imagine it works like this. So what do we want? Then we want these 6 dimensions to be compact and small enough. And that is not enough. We want them to be stabilized as well. Otherwise, we don't reproduce four-dimensional relativity because we don't want any massless scalar fields. They would violate field forces and so on. And then there's a whole laundry list, okay? We would like the 4 non-compact dimensions to be de Sitter-like, and then you can add all your particle pheno constraints, early universe cosmology, you name it. And what I want to do, as I said, I want to keep it simple. I want to stick to these 2 options, okay? So once you do that, you could say, okay, what do we want for these 4 non-compact dimensions? There's anti-de Sitter, there's Minkowski, and there's de Sitter. And let me maybe first say something about de Sitter. What is interesting is that, we're 2022, and there's still no agreement on de Sitter. I think Liam gave an excellent talk, but also Liam ended by saying, this is work in progress, okay? So we should bring it up during discussions. I think it's absolutely crucial. We talk about the status of the Sitter space, but I will not for now, okay? So then that leaves for me 2 options, Minkowski space or anti-de Sitter space as a non-compact manifold. Well, Minkowski is also problematic in a way, right? Because either I have it for theories with more than 8 supercharges or 8 or more, but then I have a moduli space, and for less, it's unclear whether that is possible, which is a version of the cosmological constant problem. So then I naturally get to this anti-de Sitter, and that is in a way great because I think anti-de Sitter space is an option, is sort of a possibility for 2 communities to come together, a phenomenological community and people doing more formal holography, okay? And that is what I want to focus on. So once we talk about anti-de Sitter, I can address the question, what did I mean with small enough extra dimension? So one obvious thing that I need to satisfy is that the Hubble scale or the ADS scale is parametrically larger than the Kaluza-Klein scale, right? If you then put an observer in such an ADS vacuum, the observer will say, hey, I only see 4 dimensions. This is not true for any of the holographic backgrounds we ever studied. Let's keep that in mind, okay? So that means we sometimes say they're not scale separated. But you see, scale separation is absolutely crucial, because if we don't have scale separation, we cannot use effective field theory. But interestingly, effective field theory is actually sort of, string phenomenology is based on between top-down and bottom-up, but it definitely relies on effective field theory Lagrangians in 4 dimensions, right? But if you cannot achieve scale separation, you cannot even follow this approach, right? So let's keep that in mind, and let's also never forget that this issue of scale separation is nothing but the cosmological constant problem in a certain form. Why? A typical flux solution, the one we study in holography, indeed has the property that the cosmological constant is of the order of the Kaluza-Klein scale. Okay? That is exactly what the cosmological constant problem is about. Namely, you expect vacuum energy to be of the order of the cutoff scale, being Kaluza-Klein. All right? So very quick, and then I'm done. I want to quickly say what are sort of conjectures about these statements of scale separation and what is the actual work done in trying to get it and whether they conflict or not. Because the swampland conjecture, they're nice in the sense that they guide us in asking certain questions and trying to do certain calculations. So the most famous one here is the following conjecture, which is called the ADS scale separation conjecture, which is telling us that if the cosmological constant goes to 0 from below, so we're talking about a series of ADS vacua, then we expect a tower of states with a characteristic mass scale m, which goes like lambda to the power alpha, where alpha is 1/2 for supersymmetric vacua. If that is true, there's no scale separation for supersymmetric vacua. Then there's the ADS moduli conjecture, which is very closely related, and that is, if you want, a weaker statement. It doesn't say anything about a tower. It just tells us that if we are able to find vacua, ADS vacua, there should always be sort of light scalar fields, right? And by light, I mean that this should be impossible. If you multiply the mass of the scalar field with the ADS length, it should not be parametrically larger than 1. Why is that an important statement? Just look at the scalar potential. Imagine you can make it really large. That means that you can take your scalar potential, you send it to 0 from below, and at the same time you squeeze it, you make the mass high. Imagine you have such a potential. The moment you break supersymmetry with an ingredient which is not too high in energy, you will have a metastable de Sitter. But we know how difficult it is to get metastable de Sitter. So it's natural to conjecture that this might not be possible. So what do we have? Of course, we have all these tour de force, this work, KKLT large volume scenario, but in a way, they never achieve scale separation parametrically. However, we heard a very nice talk by Liam saying that they can get very, very small values now, okay? So in that sense, you could call it parametric. But then we should discuss here today, do we think it's fully controlled? Could there be a tension with what is called the tadpole conjecture, which seems to gather a lot of mathematical evidence? And it was pointed out that there's even a tension with holography. What does the audience think about this? What do we have on the type 2A side? On the type 2A side, we have something which is definitely parametric, in the sense that there's a number which we can send to infinity. These are the so-called DJKT vacua, and they achieve arbitrary good scale separation at arbitrary weak coupling and arbitrary large volume. Okay? What do we think about this? Do we trust them? It was pointed out by Bobby Acharya and friends that it requires smeared orientifold planes. Do we worry about the backreaction? In fact, a lot of it's been done in the recent years, and it makes us understand it a bit better. The usual criticism was that these vacua are found in massive type 2A, but in fact, you can also get them in massless type 2A. So that means we actually should have an M-theory picture of the orientifolds and not worry so much about the backreaction of the orientifold, since we have a geometric picture. But once you lift them to M-theory, it was been pointed out that these look like Freund-Rubin vacua. And then these should be Freund-Rubin vacua, which have, an arbitrary large Kaluza-Klein mass at a fixed curvature. But it has been pointed out that such geometry has never been seen. It contradicts a lot of CFT statements, although there's not a full proof. So we should wonder, is it really making sense? And this is why I believe we need an orthogonal approach. Already for 20 years we have been doing SUGRA. Can we do holography, which is a very different way of looking at things? And in holography, the statement of scale separation means that the spectrum of the CFT is very bizarre, especially if you want an ADS vacuum that you can lift to de Sitter. There should not be any tachyons above the BF bound. So that means if we believe there is, the KKLT landscape is there in the way we think about it, the DJKT landscape, it means there should be an infinite or huge family of CFTs, which are dead-end CFTs in 3 dimensions, which have, so they don't have any relevant deformations, and they have a huge gap in the spectrum of operator dimensions. Maybe I'm going over time, so let me go to my question slide. So what I think would be good to discuss, do we really believe, is there holographic evidence for the phenotype anti-de Sitter vacua people have been discussing? Can we even exclude them in dimensions higher than 3? I'm talking about the CFTs. So can we exclude phenomenological ADS vacua in dimensions higher than 4? You might think this is a silly question. It's not at all, because it would make 4 dimensions special. I want to ask the audience, do we trust the type 2A vacua? Because they're really remarkable. They're the only string theory solutions that I know of which have this much control and these bizarre properties. And then maybe a more general question to the audience, because we have been debating these things for 20 years. What should be the objective criteria for string theories to accept moduli stabilization and de Sitter scenarios as proven facts? Okay, are there any questions? Thank you.
Questions, 1 or 2 questions for Thomas?
Yeah, I'm not totally sure if it's right to ask this now or later, but about the third thing, right? So, these problems are hard, but something that I think was useful for me and maybe should be useful for others is that, a lot of the criticism that we make of de Sitter in string theory applies equally well to attempts to construct the standard model in string theory. You can say, oh, we tried a long time, it was too hard, you have to break supersymmetry, it's hard to stabilize all the moduli. And I personally actually don't understand why there's this strong feeling that just because we haven't solved it yet, therefore it must not exist. To me, this is a very strange way of thinking about things. Why don't we just say that we think the standard model doesn't exist in string theory? That would, move on to something else, right? I feel like the evidence is equally good for the statement the standard model doesn't exist in string theory as the evidence for de Sitter doesn't exist in string theory. It seems to me it's just a hard problem. And, I enjoyed Liam's talk a lot. I agree we should discuss the validity of it, right? But if we're going to criticize it, we don't criticize it by saying it's inconsistent with some conjecture that somebody made, right? We should just look at the construction and see if it makes sense.
So first, thanks for the question. I want to say that first of all, Liam's talk was not about de Sitter. It was about anti-de Sitter. Okay. And then I want to say, I'm not sure I agree with the statement. Let me tell you, if you look at string theory talks before 98, actually there was a common belief that there was no de Sitter. Okay? I can show you statements in the literature. And nobody was making any problem because, okay, we don't see de Sitter. So the wrong attitude is that you say, oh, now we see de Sitter, so for sure it's going to work. Okay? So Shetan will say something about the evidence for de Sitter observationally. But also don't agree that it has to do with supersymmetry breaking. We have so many SUSY breaking vacua, which we actually are under control. So it's not the technical fact of breaking supersymmetry. Everybody that has been playing with de Sitter model building has seen the following thing. You get control, you can break supersymmetry, sort of okay, and for a reason that we don't understand, the moment you go to positive energies, you see things falling apart. That is just a statement from people doing model building. And then I also want to add, forget about the string theory embedding. The existence of de Sitter has also been questioned within general frameworks of effective field theory. Polyakov has been saying for a long time that there are good reasons to believe that, that the cosmology constant is running the moment it's positive. If that is true, you expect de Sitter isometries to be broken at the quantum scale. String theory is a smart theory, and maybe it's telling us that this is what we're seeing. Yeah.
I don't say de Sitter, right?
No, I'm talking metastable.
These arguments of Polyakov are just not correct, though, right? I mean, it's easy to say I don't believe this and I don't believe that, right? But I mean, I feel there are plausible constructions here, right? Like what we had this beautiful talk, and I mean, I don't know. Either these constructions are wrong or they aren't, right? I mean,
no, I disagree.
So can I make
a talk which was very convincing in a way, but we should discuss it. But then it has been pointed out that the moment you add anti-brains to it, there was a paper only 1 month ago by Blumenhagen in France. They can actually show that it's completely out of control.
But I'm trying to meet you where you want to be. Let's not.
Yeah, I think this probably is longer discussion. We should definitely come back to it over the discussion, but I think this would be longer, perhaps. So maybe we should do that after we hear from Stefan. So let's thank Thomas again.
Okay, so let me start by thanking the organizers for this nice conference and also for inviting me here. And so in the spirit of, since we have been asked to be provocative, so what I'll do is I'll start with some extreme statements and then roll them back as we go. And so, the first statement is, of course, that string theory, I think, even if we disagree about various aspects of the viability of the DS construction, I think it is certainly true that there is no consensus about the status of de Sitter in string theory. So using that as a jumping off point, I think let's take the statement that maybe string theory doesn't have de Sitter vacua at all. And then how are we going to confront the observational fact that the universe is acceleration? So I'm going to talk a bit more about the observational side because in the last couple of years I've been less working on swampland and more looking at the actual data of acceleration. And one of the observations is that all the direct observational evidence for acceleration comes from late time observations, by which I mean observations below, let's say, redshift of about 1. So, and observations at late times are the least reliable. And there is, and one objective quantifier of that statement is that there is about 4 to 6 sigma discrepancy in the measurement of the local value of the Hubble constant, which is based, if you compare between deep redshift, let's say from the CMBs at redshift of 1100 and the local measurements of redshift. And this is one reason why you may not want to consider the possibility that the tensions between early and late time measurements, and these precisely the same observations, the observations that based on supernovae are what are in fact responsible for the conclusion that the universe accelerates as well. So this might make you a bit worried. And so the general attitude of cosmologists is that CMB data from WMAP and Planck satellites, which is believed to be more clean and pristine, coming from the early universe, whereas the observations of late time cosmology are generally speaking ugly and messy. And this is the same type 1A. So this is something I already mentioned, which is that the same type 1A supernovae that are responsible for H0 tension are also the ones that are largely are what we base our conclusion of the accelerating universe. So given these conflicting hints, I also should say that there is multiple pieces of evidence for H0 tension, and the systematics are not exactly the same in each of them. But given these conflicting hints, and the fact that it has been difficult to get de Sitter vacua in string theory, how seriously should one take acceleration of the universe? Because if it is the direct observational test, I emphasize, is largely from late time observations. So the point, however, is that even though that is true, the conclusion still, I think, is basically that we should probably take it seriously. This is a conclusion I'm sure that many of you anyway believe. But I think it is good to go back and look at it, taking theory seriously rather than observation seriously. And so there are the circumstantial evidence for the indirect evidence for acceleration, I think, is compelling. And even if the late time observations, as I will say, is still quite unresolved, the H0 tension, I would say. So there are three things I think are the basic observational pieces which go into the claim that the universe is accelerating. And the first one is the flatness, and that you can see in the power spectrum of the CMB. And then there is the fact that these are the classic facts which compelled people into believing that the universe is accelerating when it first happened when we realized that in the beginning of the century. So one of them is that the universe contains stars which are sufficiently old, and then there is also the fact that there is galaxy counts. Let me not get into that. So, and then there is the fact that the prediction, it was an actual genuine prediction by Weinberg that the acceleration of if cosmological constant should not, anthropically at least, it should be around what we are actually observing. So these were good reasons to be convinced, and they are still good reasons, even though the actual late-time direct observations, I would say, are not as good as they probably should be, considering the controversial nature of the conclusion that we're drawing from it. So, and also the evidence is slightly stronger now, but not significantly stronger. And you can draw this, there is some evidence for this from, the power spectrum of galaxy distributions, as well as secondary anisotropies of CMB, and even more supernovae come to the same conclusion. But there have also been criticisms of whether these evidence, these extra new pieces of evidence are as reliable as what they used to be, or as they should be. And if you want to take a look, I forgot to put a reference here, you can take a look at Subir Sarkar's talks. There is the counterpoint. I'm not necessarily suggesting that as the standard. So what is the most conservative resolution of this H0 tension? And I think that there is no particularly compelling evidence that I can see. H0 tension is either systematics, which is, it's not so clear that it should be systematics because there is multiple pieces of evidence. It cannot be, one set of systematics cannot fully explain what the H0 tension is, because we have evidence for it not just from supernovae, but also from other pieces of data. So I can say more about that if necessary. And then another possibility is that probably there is late time small breakdowns of FLRW, and that is what is partially responsible for this zero tension. And I have looked at that in the last couple of years, but I find that that's not sufficient to, it's not clear to me that that is fully sufficient to explain away the zero tension. And the final possibility that is often considered is early dark energy, which is a period of accelerated expansion right before recombination. And that might be enough to, that can raise the H0 value, is another possibility. But there have been, criticisms of that from, even though the H0 tension is resolved in some sense, it actually makes other tensions worse. And there have also been, even from a string swampland point of view, I think Tom Rudiles has a paper where he basically talks about how the axionic models of early dark energy cannot really be, they are probably in the swampland. So there are criticisms of that kind. So it's not completely clear where the whole thing will land. But despite all this, considering the circumstantial evidence and the indirect hints, I think it is fair to assume that the universe still accelerates. And so probably one cannot avoid confronting that in string theory. And so given that, so obviously this is a statement that is perhaps not surprising, but I think that given that, so again in the same spirit of trying to consider, let's say, extreme ways of how to handle this fact. So one could possibly look at, so instead of looking at string metastable de Sitter states as Thomas was talking about in his talk, there could be non-standard constructions. I have put some references here, but I'm not necessarily, all of them are in various forms of, they're not nowhere near as elaborate as, or at least as developed as the metastable vacuum construction attempts. But one simple paradigm that I would like to kind of promote is, which, as many of the experts here already know about it, is the idea that maybe the DS bubble wall between because swampland already predicts for you anyway, unstable ADS is, non-supersymmetric ADS is in the swampland, and non-supersymmetric ADS always has to be unstable. And if it decays into a supersymmetric ADS, then in a non-perturbative decay, so then you can always have this possibility that there is a bubble wall between these two phases. It's a first-order phase transition, and it is a well-known fact from very long ago that you have shells which are, it's kind of like a Randall-Sundaram generalization where you have a de Sitter on the wall. So, and this scenario has been, revitalized by these people, and I think that is something that probably is kind of interesting to consider. And in particular, I think it will be interesting to consider the possibility that are there non-supersymmetric ADS vacua which have only non-perturbative instabilities. So I think that will be an interesting question from a swampland and landscape kind of point of view. And I think I have probably overshot my time a little bit, so let me leave these questions here and stop there.
One or two questions for Chetan. Any questions?
I maybe have a question. It's about since you say you have a preference for the de Sitter bubble model, like something I don't understand about this model is how do you localize gravity on the brain, right? Like this is.
I don't think it is. It's not fully understood. Right. I would say that. I think that it is. That's a good question. I think. It's not my.
I know.
But at the same time, I do think that. So it is non-trivial that the evolution equation that they get is actually. The one that descends from Einstein gravity. So that I think is non-trivial. And I think you can look at, for instance, the Gauss-Karachi type of relation, and it follows the structure that you get in Einstein gravity, which is somewhat non-trivial. So, but that's not quite answering your question. Okay. But nonetheless, I think it is an interesting sort of first step. Yeah.
This works? You can hear me? I just wanted to comment on it. Mm-hmm. So the way gravity is localized is vastly different from the Randall-Sundaram scenario.
Right.
And they have done various tests.
I don't think it is localized necessarily. Is it clear that it is localized?
So far, every single test has passed, but what you need to do is you need to look at what creates matter on the brain.
Yeah.
And then to actually solve the problem of how it attracts itself on the brain, you need to look at the full back reaction. So it has been done for various sources, and each single time they actually get Einstein gravity in the usual way. Yeah, but I guess more work needs to be done.
Yeah. So also there is this question one could ask whether, because of this there is a boundary-like thing. I mean, whether the graviton is massive, but I don't think it is. So yeah, I mean, I think it's a fairly open question, but I think.
Any other questions? Okay, if not, let's thank Chetan again. Okay, so now we put in the questions that, this is the list of questions that each one of us raised, all summarized here. So you're welcome to, discuss any of these topics as suggested topics or any other topic that you would like to raise. It's completely open, informal, and now we can be a longer discussion. We have whatever time we need. Again, I remind you, if you want to direct it to a specific person in the panel, say so. If it's a whole panel, just say it's for the whole panel. And if it's just a comment, say it's a comment. So let's start discussion. Leon has a question.
I wanted to come back to an excellent point about the Dantle rays earlier on. This is, I guess, largely for Thomas, but partially for the whole panel. And since our scope here, I guess, is string theory in the real world, it seems reasonable to talk about the standard model in string theory. And really getting the standard model in string theory would mean finding not just the right gauge group, the right matter representations, but the right masses, and doing so in an actual bona fide vacuum of string theory, and then crucially showing that the moduli are well above the excluded scales. So typically, for typical early universe cosmology, well above about 30 TeV. And this falls into the 95% of string pheno solutions that Thomas was talking about. It requires that one have vacua, explicit string vacua, with some degree of scale separation and all moduli stabilized. Now, I don't think we need to decide whether this is exactly as hard as de Sitter, but we've been at it for decades and it's not solved. So it's certainly hard enough to be worth mentioning. And I'm curious what people's perspective is on why this problem doesn't need to be attacked, or why it should be thought of differently than the problem of de Sitter.
I'm happy to first try to give you an answer. So first of all, I guess, well, my take on standard model building would be that it's a bit empty without first stabilizing your moduli. So that's a nice thing about string theory. It's difficult to decouple particle physics from cosmology. That's actually a very good sign of string theory. So this is why, yeah, I think one has to first stabilize moduli and then ask this question about the standard model. But so I very much disagree with the point of view of Daniel, because it's not at all like because standard model building was difficult that we gonna have a conjecture against it. What happened with this sitter was very different. Okay, so first of all, there's a very common misconception. The conjectures about the sitter made, first of all, rule them out in a weakly coupled and parametrically controlled regime, which I hope that our field finally has reached consensus that seems to be the case. So I don't understand the sensitivity that people have with these de Sitter conjectures from that point of view. Secondly, there's a lot of heuristics behind it, which seems to work out. In the original paper by Cumrun, there was an argument based on entropy, on counting degrees of freedom, and then interestingly, you see this realized in actual potentials that you get when you have control over the compactification. So whatever thoughts have arisen or have happened in the last couple of years, they're based on a lot of intuition backed up with heuristics, and I think that's very different from the fact that we haven't made conjectures about the existence of the standard model, right? I'm not sure whether I sufficiently answered your question, but
can I maybe add something? So I think these are two very, these are questions which are not at the same level, right? The question of whether we get de Sitter string theory, it's a qualitative question. We're not yet asking to get the real world. We're asking, is there a de Sitter solution in string theory? If you wanted to ask an analogous question for the standard model, it would be, a similar question would be, can we get chiral matter? Can we get SUSY breaking? Can we get Higgsing? Can we get a hierarchy for the Yukawas? And we can get all of those things separately. Right?
But that's an artificial separation between the moduli stabilization problem and the standard model problem in the case of the standard model, but not in the case of de Sitter, which is, I think, the entirety of Daniel's point there, and also my point, which is that really getting the standard model in any realistic sense is inseparable from stabilizing the model, as is the case with de Sitter. So I don't quite understand why they're not being measured in the same way.
I think we would all be happy we just have and I think this is, for instance, where your work is going, right? To get a de Sitter, like just any de Sitter, right? Even if we suppose somebody tomorrow comes with a de Sitter which is not scale separated, which is as bad as one can for phenomenology, it would still be great. I would be very happy, right? We're just looking for one feature still, and that's the one feature we cannot find.
Yeah. I agree also with the comments made. I don't agree with Daniel's question, at least philosophy in that case. We cannot say that you cannot do anything unless you do everything. That's the way he sounded like. And I mean, there are, as Miguel nicely said, there are pieces of everything that we know in the sound model which is realized. And so you can ask similar questions about one aspect of it or the other. It's not like to say that this is necessarily related to getting SU3 cross SU2 cross U1 is necessarily related to the dark energy. It's necessarily related to that. That's too much. There could be connections between some of these facts, but we already know we can break supersymmetry, we can have dark energy, we can have unstable in that case, we can have this and that. So the question is, to what extent can we get a metastable de Sitter or whatnot? I think is a fair question if we don't say specifically which dimension and all that. It is a puzzle that we do have metastable ADS, no problem, breaking supersymmetry, no problem, but we don't have a similar one for de Sitter. And so those are fair questions, I think.
It's a question for Thomas or anyone in the panel. Can you remind us of Polyakov's argument against de Sitter and how you think it might relate to the conjectures that you guys now have for de Sitter?
You mean Polyakov's argument?
Polyakov, yeah.
Okay, so like most people in the audience who have attempted to read the papers, I have not fully succeeded, but I can at least give you a simplified picture, okay? So I think, but people should correct me if they disagree, what Polyakov would be saying, and many other people, by the way, is that you expect the cosmology constant to sort of have an RG flow, which, similar to Schwinger pair creation, Schwinger pair creation, I mean to the creation of anti-particle pairs near that can screen a charge, you expect some kind of metric creation that can actually screen the cosmological constant, okay? And of course, this effect doesn't happen the moment you assume a Bunch-Davies vacuum. But then Polyakov would first of all start his argument by saying the Bunch-Davies vacuum is not a physical vacuum. And then you could try to compute the back reaction of this particle creation. And when you compute it, you would actually rather get a runaway. So you have maybe, an accelerating cosmology, but it will, the quantum effects break the de Sitter isometries. That's one. I mean, there's a whole literature. It's Motola, it's many other people, and they all have different effects. But spiritually, it's always like this. Yeah.
So let me ask a quick question, follow up on that. So in Motola's calculation, for instance, it is the particle creation is basically reducing the lambda, right? Is that the same sort of calculation? What is the difference in Polyakov? From what you said, it sounded like the lambda is running here also.
Maybe we need Dio here, but I would say a technical difference that I remember is whether you do the calculation for massless fields or massive fields. But maybe there are actually experts in the audience that can speak up. But no. Right.
And what might that be? Okay.
I think this is a nice, the history of the instability of de Sitter is long, complicated, and I think there's a nice, what I like about this instability of de Sitter literature, which I think needs to be cleaned up, is that it's within the realm of effective field theory and perturbation theory that one can just cleanly establish whether or not that mechanism is already good enough to destabilize it. And then you don't need to conjecture anything. It just, quantum mechanics takes care of itself. And if it's not the case, it leads, for these conjectures to be true, a new mechanism to take over. So I think there's something very serious about sorting out this effective field theory. And maybe, I have a feeling it's perturbatively stable using standard effective field theory, but the final word has not been said on that. I think this is a very nice point of contact to clean up that. The other question I had was a little bit more phenomenological, because I like that now there's this dark dimension, micrometer, Question is, if that's not observed, what do we conclude?
Good question. It's actually, when we wrote that paper, we were very scared because it's so close to being ruled out already. We should be, yes. But also, of course, exciting also because we are at the border of it. I would say that when we were discussing it with collaborators, Miguel and Irene, we said that, look, we will experimentally know if the distance conjecture for the de Sitter works or not. That is what we are that's the main thing we are really putting in. So that would be exciting. And so I mean, after all, we don't have a proof of the distance conjecture for de Sitter, and most of the evidence we have is for ADS. And so that would certainly be an interesting thing to learn. So that's what I would learn. That's what I would say would be the case. But I would say that there are, let me say it a little differently with something I didn't mention during my talk, which is actually a different perspective. You see, we do have the dark energy problem regardless of what it is. It is still, we know it's quasi-stable. Whether it's actually metastable de Sitter or very slowly changing or not, we don't know. But it's, I mean, barring Shetan's point that it might be a fluke, assuming that's not the case, then we have to have a quasi-dark, stable dark energy, whatever it is. So, but then we know that everything we know in effective field theory runs against that. We have a contribution of all the particles, the Higgs, this, that, to this, and they don't cancel or whatever. There's no reason they should be canceling. But we know it does cancel in the real world. So what happened? And so that statement is actually an evidence, I would say, for the distance conjecture with de Sitter. Now, you say, how does that relate to the distance conjecture with de Sitter? The reason is that if we say that there's a tower of light particle whose mass goes like lambda to some power, that also means that lambda, the dark energy, is the mass to 1 over that power. In other words, the dark energy is determined by light modes, not the heavy modes. And that's already observed in the real world. In other words, we already know that the dark energy is not determined by the Higgs mass, electron mass, it has to be much lighter. And so that's already, I would say, one evidence in the favor of dark energy. Now, actually, if you look back at the literature in string theory, we already have evidence for this. The statement that the lambda goes like some power of light scale, and somehow there's a screening going on, canceling the masses of these heavy modes. What evidence do we have? Well, Take for example, a weak coupling string. In fact, take extreme weak coupling of the string. G string goes to 0. The cosmological constant in that limit is identically 0 in every string theory. Now, you might think it has to do with supersymmetry or anything. Actually, no. It's even true for bosonic string theory. In bosonic string theory, the lambda is exactly 0 at string coupling going to 0. Now, what's the reason for that? Well, there are various ways of saying it, but I think probably Witten said it the best way in the mid-80s, that you can think about that as coming from conformal invariance of the worksheet. Namely, if you compute the genus 0 answer, that's whatever number it is, it's a finite number, you have to divide out by the volume of SL2C, which is infinite. So you get 1 over infinity, you get, or constant over infinity, you get 0. So the fact that the cosmological constant is 0 is already quite remarkably related to a bizarre fact of string theory, which is conformal invariance. So the fact that potentials that we always draw for scalars has to go to 0, not to a constant, which is not obvious from the effective field theory, already is rooted in one of the fundamental principles of string theory, conformal invariance. And now, you could say, well, this is just genus, this is strictly G equals to 0 limit. What about the correction? For example, you can take the O16 cross O16 string, in which that you can go to the next order, compute the one loop correction. Again, you find the one loop correction goes like, so in the limit of G string goes to 0, goes like the power m to the power of 10, where the m is the string scale. Again, you're cutting it off by the string scale, which are the light modes as G string goes to 0, not the Planck scale, not 100 times m string. It is not because string perturbation theory is breaking down, because if G string is sufficiently small, 100 times m string or 10,000 times m string are still within the realm of perturbative string theory. But the contribution scales like the lightest mode, like m string to the power of 10, not 10 billion m string to the power of 10. Why is that? Well, that follows from SL2Z symmetry of the torus. Namely, again, when you try to do the effective field theory, you see that the higher modes, their contribution are recounted in terms of the light modes. So that means that when you're doing the lightest modes, somehow it's repackaging the higher mode contribution, in this case by this amazing symmetry, which is not apparent from effective field theory, but it's true in string theory. So I would say that these are evidences for the distance conjecture for de Sitter. And that's what, we have already some evidence in this context. There's a question there.
So I have a question for Cumrun and one for everybody. So if we are in this dark dimension scenario at some energy that is between the Kaluza-Klein scale of the dark dimension and the Kaluza-Klein scale of the very small other dimension, that my effective description is just 5-dimensional, much like the original Kaluza-Klein theory. So do I have stability problems coming from Witten's bubble of nothing?
Do we have an instability of bubble of nothing? Is that what you mentioned?
Yeah, that's my question for you, and then I also have one for everybody.
Well, as Miguel was saying, the cobordism conjecture, for example, which is the generalization of the no global symmetries, already suggests that any theory of gravity, including supersymmetric or non-supersymmetric, will have a bubble of nothing in it. So the question would be is that we do not know what's the corresponding energy scale associated with such a tension of such a domain wall. So that's the first answer to that. So we don't know what it would be in this case specifically. It could be Planckian, it could be higher dimensional Planck scale. We don't know. That was your question, correct?
Yes, thank you.
Maybe I can add something. So we had this paper with Iñaki, Irene Kepa a few years ago, where we were trying to construct bubbles of nothing very generally in string compactifications. And what we were, so we have specific models where the bubble of nothing had weird topologies. And in that model, what we found is that the effective tension of the domain wall is controlled by something like the Susy breaking scale of the model. So that was something very geometric, but one would perhaps if one extrapolates something like that, you get something like that also in the dark dimension scenario. So I would say if there's a bubble of nothing, or also from cobordism conjecture, you would expect that the tension of whichever domain wall you have is below the fundamental Planck scale at least. So that's the 10 to the 10 GeV in this model.
Okay, thank you. Let me quickly ask the other one. It's about the de Sitter. So it was proposed that maybe the de Sitter doesn't come directly from modular stabilization, but it comes from radiative correction that you have between KK scale and low scale by some normalization group effect. What do you think about that?
So I actually didn't understand. There's like some back reaction.
No, I think Fede, I'll try to repeat the question. You tell me if it's wrong. This is a paper that suggested that you actually, if you look at an ADS vacuum from a far distance, so you run an RG flow, that it actually becomes a sitter.
Yes,
right?
exactly. Yes.
Yeah. There was a paper by Senarat de Alois, I think. Right?
Yes.
Yeah.
So you have an ADS vacuum and you look at it at long distances, it becomes the sitter.
So that's an extreme example of RG running off the cosmological constant.
Yeah, so you have ADS at KK scale, and then you have RG running from KK to very lower scale, and the RG effect will make you the sitter uplift. What do you think about that?
So what we have is the mechanism that Cumrun was explaining. Okay, that relating the tower of states to the vacuum energy, it's a mechanism involving the IR vacuum energy, right? Like, what is the UV vacuum energy is something that is perhaps not so well defined, because how do you see vacuum energies? Because it gravitates, and gravitates at long energies, right? So in the end, we measure the cosmological constant because we see some deep IR curvature of the universe, right? So I think with this, the mechanism that we have would be just for the IR. I'm not sure. I'm not sure how to make sense of RG flow of the cosmological constant, because the way I measure it is with gravity. But maybe somebody else has ideas.
I think there is a slightly more conservative paper, I think by Jombi and Perlmutter, where they do a relevant deformation of some ABJM type of thing, and in the infrared they break supersymmetry. It's not de Sitter, but what is the status of that? I think it was like almost 4 or 5 years ago. Is it it's supposed to be a stable supersymmetric, non-supersymmetric vacuum? Is there anything known about that?
You mean in quantum field theory, or?
Yeah, it's in quantum field theory. So it's it's an ABJM, so it's a superconformal theory, and then there's a relevant deformation, and the claim is that it ends up in the infrared, giving rise to a supersymmetry breaking vacuum, but which is, at least they can't find any obvious instabilities. So I was just wondering, because there's various statements about the instability of non-supersymmetric things, is there anything more?
So the universal instability, I think, is a gravity statement, right? But also, like, for instance, anytime you have a supersymmetric field theory, right? The way supersymmetric means there's some SUSY vacuum somewhere in moduli space. If you can find a non-supersymmetric vacuum, it's still going to be unstable, right? There's going to be a Coleman-de Luce bubble,
right,
on the nose.
No, but the claim that they are making, I distinctly remember it as the claim was that it doesn't have any kind of this thing. So
right. But
the possibility is that maybe the supersymmetry is broken spontaneously anyway. Right, that's a possibility.
Right. What I'm saying is that if there's no SUSY vacuum anywhere, I would just describe that as a model where you have perhaps just something supersymmetric in the UV, and there's like explicit deformations that break supersymmetry, right? And then the IR flows to something non-supersymmetric. And we do have examples of exactly stable quantum field theories which are non-supersymmetric, like the free scalar field, right? Like, there's no, these are all quantum gravity statements. If correct, they're quantum gravity statements, certainly.
Right, but I mean, because these have holographic duals, that's the reason why, these are supposed to be flows which have, are holographic duals of perceived, ADS kind of systems, right? That's the reason I'm asking.
Right. I don't think there's a claim that non-supersymmetric quantum field theories do not exist. Right. The claim would be that if you have something which is non-supersymmetric, has a Larsen limit, like the OM vector model, the holographic dual wouldn't be Einstein.
Right. Yeah. No, I agree. Yeah.
But I think that would.
Okay. So I think so. Your answer would be basically that this deformation eventually in the infrared, it might be dual to a non-Einstein.
Yeah. Okay. Well, if there is a Larsen limit, if there's a small limit.
Thank you. Hi, so I had a comment and a question on these de Sitter bubbles, sorry. So first I wanted to mention that there are some explicit candidates for these de Sitter brane worlds, in particular in the O16 heterotic string, but I think we really need to, make completely sure that there are no perturbative instabilities. It seems to be that way, but we're not certain. But my question, I guess maybe mainly for Cumrun and Miguel, is could such a de Sitter brane world be compatible with the dark dimension? Namely, could the standard model brane, so to speak, be such a brane and the bulk be ADS instead of DS, which would actually solve the issue of having to deal with de Sitter distance conjecture and going back to an ADS.
So, did I understand? Are you talking about de Sitter being the end of the world brane? Did I hear that right, or what?
Well, not necessarily an end of the world, but the standard model brane, where the standard model is localized in dark dimension. If that brane were rather expanding inside an ADS bulk.
Similar to, inside ADS bubble. It's not unlike the Randall-Sundrum discussion we had, right? What you're raising.
Yeah, I'm connecting to that.
Yeah, you mean like in Chetan's, like in Chetan's, the model that he mentioned earlier.
So I think those, as I said, the problem there, and I think Andreas had this beautiful review today. From what I understand, that the localization of the gravity on these kind of contexts is not really accomplished. That's my understanding from what I talked with Andreas about. But and the main question is that you have to understand this within the string theory context, where we could be sure that we can have a quantum gravity, some kind of a gravitational mode bound to it. Otherwise that doesn't work. So writing a model is not enough. You have to actually see that's realized in some kind of a thing you trust in string theory.
Yeah, so maybe if I can add something. So this kind of models, right, like Thomas was explaining how you can get matter which has reasonable gravitational forces and electromagnetic forces. And the way they do this, they imagine the bubble expanding, and here comes a string which is perhaps attached to some other bubble, and they can show actually that if you have two such strings, they're going to have nice forces like 1/r² localized to the brane and so on and so forth. But for instance, something that naively comes out wrong, I think, is the fluctuations of the brane. So the brane is expanding, but it's going to have some scalar fields that fluctuate, and I thought that those are actually, they are kind of like self-repulsive. They behave like self-repulsive fields. So I think it's difficult to embed this.
I mean, maybe Thomas can confirm or confute, but I thought I understood that precisely those fluctuations were shown to be described by covariant Einstein equations. I mean, it's still an on-shell statement, not an off-shell statement.
Since my PhD student was on the paper, I have to emphasize that problem at least has not been seen. And so far, as I said, they always obey the normal Einstein equations.
With plus T mu nu instead of minus T mu nu.
Yeah, exactly. This is understood. The sign of T mu nu is understood.
There is a question there. Here.
I just wanted to make a comment some of the questions of Thomas about when do we stop thinking of de Sitter, and also regarding the comments that appear. Well, first, I just wanted to say that I also agree that I think it's a different question to ask about the standard model or dark energy. But I think the best way to phrase it is something that we all agree, that the qualitative difference is to ask some local question, like the gauge group, the charges, and so on, or some global question in which you need to have the full compactification. And the point is that it makes sense, right? Like, because in string phenomenology, we've been very good, realizing engineering different parts, but it's precisely the problem, and all the Swampland constraints come when you try to put everything together, which is precisely when gravity is dynamical. So if you expect to have in a constraint, it's never going to be about something that is localized. It's always about the global thing. And that's the exciting part. I mean, that's where we have to put the emphasis, no? Like, it's not about particle physics or cosmology. It's about trying to put the pieces together and understanding when quantum gravity imposes some restriction in comparison to quantum field theory or not. And then when to stop, I think the debate is good because there's been a lot of progress in recent years, which is amazing. And I think the problem is precisely when there is no debate, and that we've been many years in which no progress was made because you just accept it. And I think de Sitter is a very important question that we have to make sure that whether it's there or not. And I think, for me, Well, a way to stop maybe is to understand better these scale separation ideas. I think this is a very promising and very nice area. But probably the moment to stop is the moment in which we learn something about the jitter, no? Like, I mean, I would expect that if we find the jitter in the string theory, we are gonna learn a lot about the jitter in quantum gravity. In the same way that with ADS, right, we learn holography, we learn many things. If we don't learn anything with these constructions in that sense, I don't think we are done, right? Like, we should try to use it to learn new things about the jitter. And once we learn these things, then this will be like a new era or a new, I mean, that's this will also tell us how to continue, no? So I don't think we have to stop until we learn something new about it.
Yes, I think I agree with Irene about this, regardless of what it is, we're going to learn something about the jitter, of what it means, and so I think that's the effort, definitely worth whatever discussion, debate, or whatever we have. I disagree with Daniel, like, well, we know it happens, who cares? I mean, that to me is a defeatist attitude.
Let me just give one example of what you said, and I hate to advertise my own work, so forget about that's my work. So there is, imagine this bubble scenario is correct, and Cumrun correctly said, well, first you show me how exactly you get it from string theory, but let us forget that for a moment. What is amazing is that you actually learn something from about the jitter. So in that scenario, you can show unambiguously, you can resolve the issue of what is a quantum state, which is an open question in quantum cosmology. And there it comes out as a Vilenkin quantum state without any doubt. Does that mean that, it's inconsistent to use Hartle-Hawking or anything else? I don't say that, but at least it shows that if you get something with a UV complete picture, you can answer questions which cosmologists have not been able to answer before. That's a model where, because you have a UV complete picture, you can say this is the quantum state and no other one, right? And then I wanted to make a maybe too controversial sociological statement about, we see the jitter, we need to get the jitter. I think there was something very similar going on a few years ago with, gravitational waves, primordial gravitational waves. I think, honestly, that as a community, we missed an opportunity because we knew from model building how difficult it was to have detectable tensor modes. Mm-hmm. And it became a common belief. Like, clearly string theory was not liking them. And right before BICEP, we were hoping to have it also, because it would be nice. But I think we missed an opportunity to actually say, and actually Joe Conlon wrote a paper before saying, this is not going to happen, people. And I think we as a string community could have actually said, we make a non-prediction. They will never detect R. And I'm just saying, so you have to be bold sometimes, right? Yeah.
Question here.
I'm not sure if that last comment also applies for low energy SUSY, but the question I had was more about quantum de Sitter. Perhaps, I'd like insight from any of you, actually, on this question. In string theory, especially in the perturbative limit, really one of the basic observables that it does for us is produce an S matrix. And this S matrix is a function of continuous parameters. It involves an enormous infinite dimensional Hilbert space. Whereas from slightly different lines of argumentation, de Sitter involves far fewer states, it seems. And I don't know whether this part of the story appears from your side, where you have infinite towers of particles, you have a perturbative stringy picture where you might imagine infinite states.
No, actually, that is what he was referring to. In the context of refined de Sitter conjecture, the paper where we show that that's an actually important ingredient in trying to argue for it. So the entropy of de Sitter was important in that discussion. So that has been aroused come up in the discussion of the de Sitter conjecture.
Just to sharpen my question, do you have in your is there a picture, you have an idea or a picture of the de Sitter microstate that there exists such a thing?
Yeah. So the idea, well, what it is, we don't know, of course, but the idea that the potential going down gives you a tower of light state, and that light state gives you that entropy was something that matched nicely with the de Sitter conjecture, the statement that potential should fall off exponentially with the distance, and that is related to the tower arising, and that tower is the entropy of this. They're matched beautifully. That was the.
I see. So then there is some concrete idea proposal from this perspective about what constitutes at least
in some limits, in what I would call in the weak coupling limits, but we don't have it in every region. So we don't have a full description, but some regions.
Yeah, in connection to that, maybe I'd like to bring up like there's been a recent series of papers, I think, by Tom and other people about the converse statement, right? Like, why do you expect that? As you were saying, string theory is a S-matrix theory, right? And so it's very natural if I start doing string theory constructions, I'm gonna end up having things that have some sort of S-matrix description. Maybe not exactly Minkowski. For instance, like the O16, O16, there's still a potential, but because it goes to weak coupling, you actually can have out states. And so you can try to do, you can compute matrix elements a la S-matrix, like via Schwinger-Keldysh and that kind of story. And if something like that is true, you would expect that in string theory you only get, or things that you can connect easily to string theory, you will only get situations where the expansion decelerates in the late futures, where you have a potential which has a large gradient. Because precisely when you have a large gradient, it's when you can construct the out states. And that could be a motivation for the de Sitter conjecture, I think. It's also related, I think Tom also relates to some energy conditions, I think.
Leon has a question.
This is back to the point Thomas made about missed opportunity in terms of primordial tensors. I do agree that that as a community we missed an opportunity, but not, I think, because of any mistaken choices, but rather because as a community we weren't powerful enough to prove rigorously, I don't mean in the sense of mathematical physics, but to give overwhelming evidence that there either are or are not good constructions of large field inflation. After all, we seem to all agree that the issue of de Sitter is relatively unresolved, and a fortiori, so then is inflation, and even more so large field inflation. And so I think it would have been irresponsible for any of us to take a public position that string theory does or does not predict a specific thing, either in 2014 or now for that point. However, it is a really key opportunity, I think still now, even though we now know we live in a universe, we didn't know this 10 years ago, we know we live in a universe in which the primordial tensors are small. I think it would be wonderful to try to prove that that either can or cannot happen in string theory. And we have lots of conjectural evidence and hard to do evidence and partial constructions, but, you know, to really settle it, I think that would be wonderful. It's an important open question in my view.
Yeah, but Leon, I think that it's one thing to say we didn't have a proof. The other one, we didn't have evidence. We had a lot of evidence that that's not the case. But to say that,
equally good evidence from the construction.
No, I think that let me say it better. The bulk of the community in Swampland was energized by that prediction that was later verified not to be the true in the context of bicep. That actually was one of the things that actually led to the belief that, come on, we should take ourselves seriously. I think the idea that in string theory we have nothing new to add to experiments just to basically just fix one of the parameters somehow a little here or there is, I think, is in some sense a defeatist attitude. We cannot be saying we can prove this is blah, blah, blah. That I agree with you. But we certainly could have said we have evidence that this is going to be very bizarre. That we should have said, that we could have said, and I think that's a mistake we didn't say.
I think it would have been irresponsible for us to...
Well, disagreed. I disagree with that. I disagree with that.
I think it's good that as a community there wasn't such a statement.
We had zero statement. That's bad. I think we were not present in the discussion. That's bad, in my view. We just were silent.
But I think what Cumrun is trying to say is that you have to always be scientifically correct, but if you say that it looks hard, and it always has looked hard, and we have an intuition that there are good reasons that might not work, that is a correct scientific statement to say. It's not the same. That's not the same as saying there's a proof against it, right?
Yeah, but I think that was actually the broad consensus of the community that it looks hard.
Right.
Right, and I think that's remains the statement. What I was remarking was that it would be valuable for us to try to nail this in a more solid way and really see whether one can show that it really can't happen or really can happen. I know it's too late compared to the experiment, but we can still learn something.
Yeah, thanks. So, yeah, I mean, I think I agree with Liam on this, that we should be, I mean, just in general, honest about what we can or cannot say. And I agree with Liam that at the time, and even now, it's not entirely clear whether large field inflation, small field inflation, any of these things can be realized in quantum gravity, though I do think arguments point against it, and it is definitely worth looking into further. I think, I guess a sort of tangential concern, though, if we're talking about sort of the public stance that we take on these things. I recall as an undergraduate student learning string theory, seeing many popular, articles about string theory and how there's a landscape of 10 to the 500 de Sitter vacua. And yet here we are kind of debating whether or not there is one de Sitter vacuum in string theory. So I guess, I don't know if this is a question or a comment, but I think it is something to concern ourselves with, is not taking stances that don't, in public, that don't maybe agree with what we're actually finding as a community.
Yeah. Taking stand is different from saying what we have already seen in many evidences. That's different from saying we have a proof. I think, Tom, I disagree that we shouldn't make any statements because we don't have a proof. We should certainly say what was said, that this looks very hard, and Liam says he agreed with that, but even that statement was not said that clearly, I would say. I mean, even that statement was it wasn't saying, wow, we are surprised this is happening. Wow, look at that. That was not consensus. It was saying, oh, well, Lindy had predicted this model. It sounds reasonable. Why not? We didn't ever raise a wow statement. That's surprising in literature. I don't see in print saying people in string theory saying we are surprised by the bicep result specifically. Surprised. We should have been surprised at the very least.
But everyone was surprised, right?
Nobody said that. Nobody wrote that. That's what I'm asking. That's exactly my point. We were silent. Maybe we said, oh, isn't that surprising? But let's talk about it. We didn't say in print that, look, this was very surprising from what we know. I think this is an attitude that I think we should have. It's different from saying we have proven, we have to be honest. Of course we have to be honest, Tom. Who says we should be dishonest? Come on. But what we should say is that we should also say what we have learned. And otherwise, if we have not learned anything, then what are we doing?
A comment on things being intuitively plausible and not having counterexamples versus being proven. I'm in the business of constructing large classes of Calabi-Yau manifolds. And a few years ago, I with a very good student, I did 2 times 10 to the 11 Calabi-Yau fourfold models. And out of these, a few dozen have a negative Euler characteristic. If you just search before for a model with a negative Euler characteristic, you'll never ever find it. It's very, very hard. Only when you have the complete list, you find that actually there are examples.
I guess you give it as an example that one should be careful, right? But I think we all agree. And the 2 examples we mentioned that backcorrected negatively. Actually, the example of Tom is actually proving, I think, the opposite point. I mean, there was a claim 10 to the 500 de Sitter, but there was no consensus in the field. Yet this goes into the media and it backcorrects very badly. And this criticism, by the way, about it is very naive because effective field theorists, everybody doing other things than string theory have an infinite landscape, right? They can write down any Lagrangian they want. This is an infinite landscape. But I'm just saying that, I mean, these are 2 examples where in one case we shouldn't have mentioned it because there was no consensus in the field. And in the other case, if we would have been honest, we would have said, well, it looks very difficult. And as Cumrun said, that was not even appearing in the media. Right, but we actually were able to say something. It looks very difficult to get large field inflation.
Yes.
In the loop quantum gravity community, I'm wondering whether they can even make such a statement. Right.
Actually, the connection that you mentioned about the Calabi-Yau reminded me of a story which actually gives you a slightly different perspective. So in the late 80s, the number of Calabi-Yau threefolds that people had studied was mostly negative Euler characteristic. So then I was studying in particular with some colleagues the idea about the fact that you can have a symmetry which exchanges H11 with H21, suggesting that there should be equal number of positive and negative ones. Heuristically, of course, right? We didn't have much evidence at that time. So I went and talked with Yao. I said, we are making this conjecture that the number of positive and negative ones are equal. What do you think? He says, that sounds wrong to me because we have much more negative Euler characteristic. So that's an example that sometimes our intuition might be actually lead the way, and now we know it's correct. So that's the opposite lesson, actually.
Because Yao's intuition based on examples that said they have.
Yes, but I'm saying that the examples in that case was not complete, but the intuition from physics said that that's a good question to look for, and later we found that indeed they were missing these examples. Over here.
Thank you. Yes, as we're at questioning experimental results, I wanted to ask Chetna how seriously we can question the measurement that the universe is accelerating. And there's a tension of 5 sigma to h0, but if you just assume that the cosmological constant, let's say it would be 0, what would be the tension then with the current measurements?
So I didn't quite guess the question. So can you just repeat? Sorry.
No, because your question point is maybe we should not trust this late time measurements of an accelerating universe. And okay, there's a 5 sigma tension with CMB, but
I was kind of presenting it as a bit of a, taking hints from theory and going and maybe challenging experiment. But then even though the point I was making was that even though the direct observations are late time observations, I think the indirect evidence observationally also is sufficiently compelling that there is acceleration. So that was kind of the takeaway message in some sense. I just didn't want to buy it as a prima facie fact just because astronomers tell us. So, and it's good to kind of look around on the data. And so, I think
how much wiggle room do you see when you look at the data?
How much is what, sorry?
How much wiggle room or how much do you see?
So, I really cannot place what causes H0 tension. So I think one has to have some sort of an intuition for what is the real explanation for H0 tension in order to have a real understanding of how reliable late time observations are. So the statement I was making was that the evidence for acceleration, the original evidence for acceleration came from supernovae, and supernovae are what are leading to H0 tension. And that is one fact. But at the same time, I have not found a fully compelling resolution of H0 tension yet. And I feel that the next generation of observations are probably necessary in order to fully resolve it. But luckily, one good thing about cosmology is that there is a lot of observations coming our way. So maybe that is what we should do. But I presented 3 ways in which H0 tension may ultimately get resolved, but I'm not satisfied with any of them.
No, my question is more about the cosmological constants, because you say...
Oh, you're talking about, are you trying to distinguish between cosmological constant versus vacuum energy? Is that what you're trying to do?
Yeah.
No, I was not. I was just saying that, no, I don't think that is coming from observations. I think observations are just leading to the conclusion that the universe is accelerating. I don't think there is any particular preference observationally for lambda versus, you can do some things, but I don't think that's not the resolution at which I was talking about it. I don't know whether that answered the question. Sorry.
Okay, I think we have more or less run out of time, but before concluding, let me thank again the organizers for this wonderful conference to allow such an open discussion. And as we heard from the opening of the string conference, having heated discussion is what we are here to do, and I think we accomplished that today. So thank you very much, everybody.